Today we'll learn about inverse trig functions. We talked about inverse functions earlier this year. Let's talk about one of our favorite parent functions, y equals x squared, or f of x equals x squared. Remember that an inverse function is just where we switch the x and the y, solve for y, or graphically, an inverse looks like a reflection over the line y equals x. Or if you pictured this as a see-through post-it note, and if you flipped this post-it note over so that that corner wound up down here, this graph would wind up looking like this. And so that would be the inverse of y equals x squared. What you'll notice though is that the inverse of y equals x squared is not a function because it doesn't pass the vertical line test. But we do have an inverse function called the square root of x. The only way we get away with that is by restricting the original function to just the positive square root of x. And if we only think of the positive square root of x, then we only have to think of the positive square root of x. And then we can call that a true function, like f inverse of x. The same sort of thing is going to happen with our sine and cosine function. Obviously, if this is failing the horizontal line test, then if we flip it, it's going to fail the vertical line test. So can you sort of see why the inverse sine is not a function? On your worksheet yesterday, I had you work on finding a bunch of angles, say where sine equals root 2 over 2. And I just kind of highlighted those on this graph. Like there's a lot of different values where sine equals root 2 over 2. And that means there would be a lot of y values for an x value of root 2 over 2 if we looked at the inverse. Well, that breaks the laws, right? So what we wind up doing is we have to restrict the domain of the original function so that we get an inverse that we can call the official function f inverse of x. The way they've decided to do it for inverse sine is they zoom in on just this chunk of the sine graph. That would pass the horizontal line test, right? Just the little chunk that goes from, what would it be, negative pi over 2 to pi over 2. If we go just from negative pi over 2 to pi over 2, then we'd only be looking at this chunk of the inverse. And that little chunk right there, let's redraw that. On the back of your worksheet from yesterday, you could redraw this. So we know that, for example, the sine of pi over 2 was 1. So the inverse sine of 1 would be pi over 2. Sine of 0 is 0, so inverse sine of 0 is 0. And sine of negative pi over 2 is negative 1, so inverse sine of negative 1 is negative pi over 2. And then just like this one kind of does this sort of curve to it, that's the same curve that this will have. So that's a piece of sort of a vertical sine curve, but we've only taken a chunk of it so that this passes the vertical line test. Now we can officially call that a function. That is the official graph of the function inverse sine of x. We'll do the same thing with cosine of x. It does need to be restricted a little bit differently though, right? Because if I tried to go from negative pi over 2 to pi over 2, that boy is failing the horizontal line test, yeah? So we have to restrict it a little differently. And the way they've decided that we shall do it is by going from 0 to pi. If we go just from 0 to pi on the cosine function, then that looks legit, that the inverse would pass the vertical line test. And so the official inverse function starts at negative 1 pi, because the inverse cosine of negative 1 is pi. The inverse cosine of 0 would be pi over 2, and the inverse cosine of 1 would be 0. And the shape of that graph looks like this. Now these graphs I'm not super concerned about. It's the whole idea of restricting this domain that's going to be important to us. So that's why I'm going through this is I need you to understand the idea that we've had to restrict the domain of the original function. That's what's going to be important. Finally, for tangent, it'll probably make sense to you. We can't have a bunch of outputs once we get an inverse, because when we inverse it, we know each input can only have one output. So what we do is we restrict it just to our middle branch. And if we restrict it just from negative pi over 2 to pi over 2, then we will only be looking at this middle branch of the inverse. So on your sheet, we'll have a point at 0, 0. We'll have a point at 1 pi over 4 and negative 1, negative pi over 4. We still have asymptotes, but now that we've switched the x and the y, they're horizontal asymptotes at the pi over 2's. And this is the graph of the function inverse tangent. Again, the thing I really want you to focus on is that we're narrowing that just to the negative pi over 2 to the pi over 2. And we're going to practice that a little bit. Out of those three graphs we just saw, this is probably the one that I see showing up again the most. And that's probably because it's the most interesting out of all of them. It has some asymptotes, it has something to it. This is super important to know. I don't want you mixing up inverse sine with 1 over sine. We know that 1 over sine x is the same thing as cosecant of x. That just means that instead of opposite over hypotenuse, this is hypotenuse over opposite. Whereas inverse sine is actually giving us the value of an angle. That's what we're talking about today. The value of all of these functions is an angle. The y value today is an angle. Another thing to know is that there's an alternate way to write this, because a lot of people maybe would get confused, because honestly, x to the negative 1, that notation does mean 1 over x. So that's confusing. Why would they use that same notation? Well, some people agree. Why would they use that notation? So they decided, why are we using that notation? Instead of using sine to the negative 1 of x for inverse sine, they decided, well, why don't we just call it arcsine of x, an arc cosine of x, an arctangent of x. Maybe I would have suggested invsine of x, but yeah, I wasn't around when they invented this. So they call it arcsine instead of inverse sine. And so if you ever see that notation, just know that they're talking about the inverse function. They're talking about what will the angle equal. All right, so here's the main event. We are to find the value of inverse cosine of 1/2. And you did this on your preview worksheet. You're supposed to find an angle where cosine equals 1/2. And we know that you can find lots of angles where cosine equals 1/2. The restrictions today remind us that we are only allowed to look. Do you remember where we're allowed to look for cosine? We restricted that from 0 to pi. Okay, from 0 to pi. That means if I were thinking about triangles, or if I were thinking about the graph of cosine, or if I were thinking about the unit circle, no matter what I'm thinking about, I'm only thinking about angles from 0 to pi. Often when I'm thinking of these, I'm thinking of triangles. So I'm going to think about making either a triangle in the first or the second quadrant. Well, since I'm getting a positive 1/2 for my adjacent over hypotenuse, my ka, I'm thinking that must be a first quadrant. What kind of triangle would have an adjacent over hypotenuse of 1 over 2? If you said, oh, that must be a 1, 2 square root of 3, you are correct. Making that what kind of angle? Did you say pi over 3? That is correct. And so for each of these, you have to kind of think of that restriction. Remember, for inverse sine or arc sine, it's a different restriction though, and that's because the graph was different. We had to restrict it differently. For arc sine, we have to be looking between negative 90 and 90, or negative pi over 2 and pi over 2. Again, whether you're thinking unit circle or graph or triangles, we want to think of between pi over 2 and negative pi over 2. Personally, I'm thinking triangles most of the time. So I'm thinking, okay, would this be a first or a second quadrant type triangle? Since the sign is coming out negative root 2 over 2, I'm thinking that must be a negative down in the fourth quadrant. And are you getting pi over 4 thoughts here? A 45, 45, 90, 1, 1, square root of 2. That's only where we're going to get root 2 over 2. So that would have to be a fourth quadrant pi over 4 or a negative pi over 4. Can you tell me why it would actually be incorrect to call that triangle down there 7 pi over 4 in this case? That would be a wrong answer in this case. It technically gives the same exact triangle. However, remember that my answer has to always be an angle between negative pi over 2 and pi over 2. That's how we've defined these as functions, so that there's only one answer each. And just as a reminder, for tangent, we're looking in the same place as we are looking for our sine. I'm not including the pi over 2's this time because maybe you remember tangent is undefined at the pi over 2's. Maybe you're thinking of the asymptotes. So again, I would have to think of a triangle either in the first or the fourth quadrant where the opposite over the adjacent equals root 3 over 1. Well, we'd get a negative if we were down in quadrant 4. So I'm thinking this must be quadrant 1. What angle is that? That's a 60-degree angle, another pi over 3. So these are just more examples of the same thing. Technically, you should be able to type these into your calculator, whether you're in degree or radian mode. It tells you what type of answer it'll give you, right? If you're in degree mode, it might give you an answer like 45, whereas if you're in radian mode, it might spit out whatever pi divided by 4 is. So just know that. Of course, I'll be asking you to do a lot of these with no calculator. What you'll need to remember is where to be looking for your tangent triangles, or if you're using a graph or a unit circle, which quadrant to be looking in or what part of the graph to be looking at. For tangent, I'm looking here and here. If I'm getting root 3 over 3, that's a 1 over the square root of 3. I'm thinking that must be a 30, 60, 90, specifically a 30-degree angle. And I chose the quadrant 1 because that's where I would get a positive tangent. Where am I going to get a negative tangent? I'm restricted to only quadrant 1 and 4 again. How do you get a negative tangent? Probably by going opposite over adjacent in the fourth quadrant, yeah? This one sometimes tricks me because whenever I see zeros and ones, I think it's going to be like a point on the unit circle, but not this one. For tangent, this is one that's 1, 1 square root of 2. Watch for that. That sometimes messes me up. So actually, inverse tangent of negative 1 is the angle 45, 45, 90. So that would be a pi over 4 in the fourth quadrant, so negative pi over 4. This is the idea. Notice that every time you get an answer, your answer is an angle. That could be trickier when you get down to these because we're used to saying sine of 0 is 0. And, well, maybe not so much cosine of 1, but we do have to think, oh, we're not looking for what is the sine of 0 degrees. I'm looking for where does sine of an angle equal 0? Okay, well, in sine, I'm looking in these two quadrants, which means I'm only allowed to look at one of these points. Is sine the x or the y value? Sine is the y value. And so it's looking like the y value would be 0 right here. So our answer should be what angle that is. What angle is located right there? That would be 0 radians. Let's try the same thing for cosine. Do you remember how cosine is different though? For cosine, we're not looking at quadrants 1 and 4. That's the only one that's restricted differently. Cosine is restricted to quadrants 1 and 2. So again, I might just write out these 3 ordered pairs. All right. Remembering that cosine is always the x value. Where would I get myself an x value of -1? Happening right there. And remember that my answer is the angle. What angle does that represent over there? That is angle pi. If you had to predict what quadrant this would be in, can you tell me? Well, out of the 4 quadrants, what do we know inverse sine is going to wind up in? 1, 2, 3, or 4. If you're catching on, inverse sine is either going to be in quadrant 1 or 4. That's the rules. And if sine winds up negative, right, do you see that negative on there? That means we must be in quadrant, did you say quadrant 4? Yes. Now, if you were to type that into your calculator, inverse sine of -0.4664, you should get a quadrant 4 type angle. Your calculator knows all about these restrictions. What about for cosine though? Because for cosine, it's making me restrict to here and here. So how are you supposed to tell? Cosine comes out positive. Wouldn't cosine come out positive in both of those quadrants? Remember, cosine is the x value. Cosine is the adjacent over the hypotenuse. And back here, the adjacent over the hypotenuse would be negative. You guys remember cosine would be negative in this quadrant? So if cosine's coming out positive, like positive 0.7322, that must mean that we're in quadrant 1. And that's why there's a different restriction for cosine. So just in summary, I might just have you write that we're always going to get an angle for each of these. So for inverse sine, maybe you just want to draw yourself a little picture to remind yourself that the answer is going to be an angle between -pi/2 and pi/2. So maybe just remind yourself that quadrants 1 and 4 are up for grabs for inverse sine. For inverse cosine, your answer will always be an angle, and that angle will always be in either quadrant 1 or 2. And for inverse tangent, your answer will always be an angle, and that angle will always be in either quadrant 1 or quadrant 4.